Okay, 3.6 chain rule, part A. So chain rule has to do with composite functions. So before I actually go into chain rule, I want to talk about composite functions. Composite functions are functions made up of two other functions, basically. So example 1, suppose f of x equals 3x squared and g of x equals 4x plus 6. Now this is the notation for a composite function. They're asking me to make a new function out of f and g. Let me finish writing this. Okay, so f of g, or f composed with g, basically. So what you do is, this is going to be equal to my function f, which was 3x squared, right? But what you're going to do is, everywhere there was an x, you're going to plug this in. So basically, this becomes 3 times 4x plus 6 squared. And that's my composite function. Okay, that's it. B, same idea, only this time I'm making my function with g, and then I'm plugging in f. So, okay, if I remember from over there, right, f of x is 3x squared. So that's what's going to get plugged in for everywhere there's an x. So my new composite function here will be 4 times x plus 6. But see, I removed the x, and instead I put this in its place. Okay. You can simplify these equations when you're done creating them. This one's pretty easy. It's 12x squared plus 6. The one over here, the blue one, I'm not saying it's hard. It's just, it requires foiling. So I'm just going to leave it alone. But these are composite functions. Okay, so deriving composite functions. This is what we're doing in this section. Deriving composite functions look something like this. It's dy dx is going to equal dy du times du dx. So we're going to use a new variable per se, okay? But it's actually just a means to an end. So example 2, I tried to break this up as much as I possibly could. Let y equal 2 times u. Okay, so u is my other function. I've already made y a composite function because it's being made with u already in it. Okay, and then let u equal 3x minus 5. Well, what is y? Okay, so y is equal to 2 times u, and u is 3x minus 5. So there's my function. I can simplify this. It is 6x minus 5. So y is 6x minus 5. All right, part B. It says find dy dx by simplifying the composite function. All right, I already simplified it. No big deal. Dy dx would be the derivative. So derive the function, which should be pretty easy, right? It's just 6. The negative 5 is a constant, so it becomes 0. Okay, so far we're like, okay, nothing new here. C, now find dy du and du dx. So now we're finding dy du and du dx. Okay, so dy du. That would mean the derivative of my function y with respect to u. U is my variable that I am deriving for. So I look back up here. This is my function. So the derivative of that function 2 times u would just give me 2. Now I'm going to derive du dx. Right, I'm going to do du dx, which is the derivative of the function called u with respect to x. So I'm looking back up here, and there are x's in it, so that's fine. So derive that, and I get 3. So what I want you to see here is if I use my little formula that I have all the way on the top, I'm just going to scoot up. If I use this little formula, so I'm just going to drag this baby. Oh, well, I'll drag it anyway. I'm dragging it, I'm dragging it, I'm dragging it. I lost it, I lost it, I lost it. Oh man. Alright, so there's my dy dx equals dy du times du dx. So basically what I'm saying is that my derivative, dy dx, is equal to dy du times du dx. So 2 times 3 is 6, right? Should that make sense? Of course. We already found the derivative. We found it a different way. But they're definitely the same. And that leads us to part D. Part D, I was just asking you to find dy dx, but using the formula. Okay, this is how you derive composite functions. Basically, you have to find the derivatives of both functions and multiply them. Of course, the functions aren't going to be this simple. Obviously, you wouldn't need the chain rule if they were just this simple. And that's what it's called, chain rule. And if you didn't get what I just said, this right here is part D. Okay. Example 3. Find dy dx if y equals the quantity 3x squared plus 1 squared. So A, figure out the two functions that compose y. So y is being made by two functions. We need to figure out what they are. So what is y and what is u? We're just going to keep calling it u. Okay, well, the parentheses is a really good indicator that the function in here, that's one of them. And then the squared on the outside is a good indicator that, okay, so like this had the potential of looking like this. Y equals u squared. I hope you see that. The squared, right? So the function squared, so u squared. Now my function would obviously be the stuff on the inside. 3x squared plus 1. Okay, so part B, again, I split it up. Find dy du. So dy du would lead me to finding the derivative of u squared. So that would be 2 times u. Now I'm going to do du dx. So du dx, du dx. So I'm going to derive the function u, right? Here's u. With respect to x, so 3x squared becomes 6x, and then the 1 becomes 0 because it's a constant. All right, so here are my derivatives. So now I'm finding dy dx. Okay, so let me go ahead and recall my little formula. Okay, so I pasted my formula here. Dy over dx equals dy du times du dx. So now remember, that's basically the derivatives of the two functions being multiplied. That's all it is. So let me go ahead and like fill this out. So dy dx equals dy du. Okay, so here's dy du to u times du dx, which is all this, 6x. All right, so that's got a problem. Dy dx is the derivative of the function y with respect to x. U is not x. U is a function made up of x, or made with x, but it's not actually x. So I can't leave it that way. So that's going to be a problem. So I got to fix it. No big deal. Let me extend this. Okay. I still want to see my functions. There they are. So let's call this now 2 times u. But what is u? So I look up here. Well, here's u. U is 3x squared plus 1. So 3x squared plus 1. So now I got rid of the u and I have x's. Yay, which is a good thing. And then times 6x. Okay, no problems here because this is fine. This is okay. They're all x's. Well, what we just did is basically the derivative of this composite function, but by writing it out this way, I can show you the rule, basically, for chain rule. Now, if I need you to look, right? The beginning part here. I need a highlighter. The beginning part here, this 2, 3x squared plus 1. I need you to notice that basically that is the derivative of the original function. So let me come up here. See? 3x squared plus 1. Imagine that was one big fat x. What would you do with the 2? You would bring it out to the front, right? Okay. So there's my 2 in the front. And then the 3x squared plus 1, which I said imagine is a big fat x. Well, there's that function. But then the 6x, I need another color. No, let's do blue. The 6x, which is right here, that is the derivative of 3x squared plus 1. That is the derivative of the stuff that was inside. Well, I can't highlight over green. Oh, whatever. So basically, what I have here is the derivative of the outer function, which was the squared part, times the derivative of the inner function. Ladies and gentlemen, this is the chain rule. This is the rule for chain rule. This is how we're going to do the more complicated equations. It's the derivative of the outside times the derivative of the inside. Now notice, the 3x squared plus 1 still looks like the original equation. I didn't change that. When it gets changed is when you do the derivative of it. All right. The chain rule. This is how I'm going to refer to it. I'm going to refer to it as derivative of the outside times the derivative of the inside, just like what I wrote before. Faster way to say it is just derivative of the outside times the inside. Whatever. But it's the derivative of the outside times derivative of the inside. And basically, if y equals f of g of x, so basically, if it is a composite function, then dy dx equals the derivative of f, which is the outside function, with g inside of it, right? And then the derivative of the inside function. Okay? All right, so example 4. I can't express this enough. This is a no foiling, oops, a no foiling zone. We will not be foiling this. Please don't ever foil this. Look at it. It's to the 8th power. Why would you do that to yourself? Like, seriously. So derive f of x equals 2 times x squared plus 8x plus 9 to the 8th power. And that's on purpose, because I don't want you to FOIL it. I want you to use the chain rule. And the chain rule is the derivative of the outside times the derivative of the inside. So hopefully you've realized, oh, the stuff inside the parentheses, that would be the inside. And we're going to call the inside u, if you hadn't caught up on that yet. U. So now the outside. Well, the outside, I'm going to rewrite this. I'm going to be like, okay, so this is 2u to the 8th power. So now all you got to do is derive the outside, multiply it by the derivative of the inside. So proper notation, I'm deriving, therefore f prime of x. That's going to equal, okay, so what's the derivative of the outside? And this is the outside. Outside. All right. So bring the 8 to the front. That's 8 times 2 is 16. U, and then subtract 1, 7. Okay. Times the derivative of the inside. Now the derivative of the inside, that's the x squared plus 8x plus 9. So let's see, let's derive that. I get 2x plus 8. And there is my derivative. But once again, I run into the fact that, oh, that's a u, that's not an x. So no bueno, can't do that. So I do actually have to plug in u. So u is, let's see, x squared plus 8x plus 9 to the 7th power. And then this is 2x plus 8. This can be simplified a little, right? The 16 in the front and the 2x plus 8, you can totally do something with that. But that's just about as far as I would go. So 16 times 2x is 32x. And then 16 times 8, 80, 48, 128. And then that's just me multiplying this with that and this with that. And that's as far as I would go. That's as far as I would make you go. The rest stays the same. It's still horrifically really big equation if I figure out what to the 7th power, what it is to 7th power. But that's it. The derivative of the outside times the derivative of the inside. That is chain rule. Right. So using the chain rule with the product rule. So here I have a chain rule, but I also have product rule. It's a combination. So okay, I need to figure out, alrighty, what are my two functions that are being multiplied? So here's u and here's v. And just like before, I do, the whole, okay, u is x cubed, u prime is 3x squared. No big deal, right? Okay, v. V is 2x minus 5. The quantity is to the 4th power. So, oh look, that 4th power. That right there is my, hello, I'm a chain rule, because there's two functions here. So what I'm going to do, I'm going to introduce another letter. We've been using u and v, right? What I'm going to introduce, it's just, it works. Part of the alphabet, we're going to use w. So I'm going to rewrite this as w to the 4th power. The stuff in here, my inner function, I'm just going to call it w. You can call it whatever you want. It's just I'm used to w. So this will be w to the 4th power. And the reason we're doing that is because this is a chain rule, and I don't want to call it u because we're already using u. And I don't want you guys to get confused. So now, v prime. That's the derivative of that function, but I decided to call it w to the 4th power. So the derivative of that is 4w cubed. So there's my v prime. Now, I don't really want to use another, oh wait, I'm sorry. Hold on a second. Before I get ahead of myself, which I almost did, w. What is w? W is the inside part of v. It's 2x minus 5. Okay, so this is a chain rule. And the rule for chain rule is the derivative of the outside times the derivative of the inside. That's how I'm going to find the derivative of v. So let me figure out what is the derivative of w. Well, the derivative of w, or w prime, or dw, w prime is fine, but I might actually write dw a lot more often. Okay, whichever. The derivative of w is 2. So when I actually find the derivative of v, I'm supposed to be doing the derivative of the outside, which is the w to the fourth power, this right here. And that's how I got 4w cubed. But then I have to multiply it by the derivative of the inside, which is my dw. You might find it helpful to do the derivative and then right after write dw as a reminder that that's the derivative of the inside. And then you can actually figure out what the function really is. Because remember, w is just a means to an end. It's not really here. Just like u and just like v. I do need to put x's back in here. So 4 times w cubed. Let's see, what is w? 2x minus 5. And that's cubed. Times dw. And that's the derivative of w, which happened to be 2. So that is my v prime. I could make it, simplify it a little, clean it up. The 2 and the 4 become 8. But that's about all I'd want you to do. So there's my v prime. So now when I actually do the derivative of f of x, and this is the product rule, and in case you forgot, u times v prime plus v times u prime. When I actually do the derivative, I'm going to still use my regular pieces. Let's see. Let's do this in yellow. I'm still going to use u. I'm still going to use u prime. I'm still going to use v, which is this. And I'm still going to use v prime. Just that v prime requires a lot more work because it's a chain rule. Because it's a composite function. So I'm still using those pieces. Nothing changed in that aspect. I'm just trying to do the derivative of composite functions. Now they're just mixing them in with product rule. Okay, so that's basically all my pieces. The rest should be familiar, I hope. So f prime of x is going to equal u, which is x cubed, times v prime, which was this big old composite function thing I found over here, 2x minus 5 cubed, plus v, which is just 2x minus 5 to the fourth power, times u prime, which is 3x squared. And there's my derivative. Can it be simplified? Sure, I would only do a little. Like, for example, the 8, bring that to the front. So it's 8x cubed. Well, I guess there's really no simplification, just rewriting it correctly. The 3x squared should come to the front. And there you go. There's my derivative. All right, example 6. Dydx of 5x minus 3 cubed times 2x plus 8. So again, product rule. So let's see. This would be u, and then this would be v. And of course, this here just means to derive this function. I'm still going to figure out my pieces, right? So u is 5x minus 3, but it's cubed. So then u prime, oh, that's a composite function. I'll get back to that. V is 2x plus 8, and then v prime is just 2. So this composite function, I'm going to have to do something with that. So let's call it something else, right? The inside stuff. I'm going to call this w cubed. So now, let me see. W is 5x minus 3. dw, which would be the derivative of w, because I'm going to need that, is going to be 5. So I need to derive. Okay. So u prime is going to be the derivative of the outside, which is the w cubed part. So that would be 3w squared times the derivative of the inside, which would be the dw. And I said to just write dw, maybe at first, until you get used to it. And now that I know what my derivative will look like, kinda. I should go ahead and plug in what w or dw actually are, or what they're supposed to be, or what they're replacing at the moment. So 3 times w, w is 5x minus 3 squared times dw, and the derivative of w was 5. So there you go. There is my u prime. I can clean it up a little because it's going to be 15, 5x minus 3 squared. So now I get to do the product rule again. And like I said before, I'm still using the same components. Okay, so u is this. So I'm totally using that. A v is this. V prime is just a 2. And then u prime just required some work, but here it is. Okay? I'm going to just do it on the bottom here. So now I can actually put my stuff together. So the derivative of that function, let's call it dy dx. So dy dx is u times v prime, which is just a 2, plus v times u prime. And that's the whole stuff we did to find the work, or this is all the work we did to find the derivative of the composite function. And basically that's the answer. I would rewrite it correctly though, like that 15 shouldn't be just smacked in the middle there. The 2 should come to the front. Actually, the 15, I can distribute that baby. So let's see, 15 times 2, that's 30x. 8 times 15, that's 80 plus 40, so that's 120. And then 5x minus 3 squared. And there you have it. There's the derivative of a composite function using product rule as well. So it's just a mixture. All right, next. Example 7 and the last example. Trigonometric functions and the chain rule. Example 7, find dy dx. Okay, so these are considered chain rule. These are fairly simple though, for right now anyway. So y equals, or a, I'm looking at a, y equals sine 2x. Okay, so figure out what is the inside function or the outside function. Hopefully you're like, oh, this is the inside function. So this is u. So this is going to be sine of u. All right, well my derivative is just basically going to be the derivative of the outside, which is the derivative of sine u, times the derivative of the inside, which is the derivative of u. It might help if you're like, okay, u is 2x. Well, du is 2. Now notice I reverted back to using u because there aren't any v's and u's here. So there's no reason for me to have to use w. If you like w, go ahead. Doesn't matter. Okay, so my derivative. So y prime is going to be the derivative of the outside. So I'm deriving sine of u. The derivative of sine is cosine. So cosine u times du. That's my chain rule right there. The derivative of the outside, which is sine u, times the derivative of the inside, which is just the derivative of u. And now I can just go ahead and plug in what the u's are, or the du's. So the cosine of u, let me look at u, here's u, it's 2x, times du, which is the 2. And of course, please write numbers, coefficients in the beginning. And there you go. There's my derivative. All right, b, same idea, different story. This stuff in here, hopefully that kind of pops out at you as being u. So u is x minus 1. So that means du is 1, right? Because the x is just going to leave a 1 behind. All right, so I'm going to rewrite this as cosine of u. Now I'm going to go ahead and derive. So y prime is going to be the derivative of the outside. So what is the derivative of cosine u? So that is negative sine u, and then times the derivative of the inside. So the derivative of u is du. We call that du. So that's basically what it's going to look like. Now I'm just going to plug in the u, and I'm going to plug in the du. See, negative sine of u, which was x minus 1, times du, which is 1. Do I really need to write times 1? I certainly hope I don't. And that is the derivative. And that's it. This is chain rule part A. We'll have chain rule part B, which will include chain rule using quotient rule. Right. Please do your homework.